Hey everyone, in our last video we showed the demonstration of falling meter sticks, and I wanted to go through kind of a derivation of showing you how we can calculate how quickly a meter stick falls based on torques. So if you look at my force diagram here, the forces that are making this thing rotate are the force of gravity. As it moves away from that midpoint, normal force is pointing straight up. You can see that there is a frictional force backwards, trying to not let the pencil slide, and those are at the pivot point. So technically, if they're at the pivot point, there's no radius, which means there's no torque provided. So gravity is causing the torque for the falling meter stick the entire time. And if you want to draw it out with those two components, the angle that the meter stick is making with the vertical is right there in my drawing. And really the only force that is causing a torque is the one that's perpendicular to the radius, which is this one right here. So it looks like mg sine of theta is causing my torque. So let's write this out. So mg sine theta is my force. I need a radius, and it's acting at half the length of the meter stick. Why are we picking half the length? Because we always said that we focus on the center of mass for objects that aren't just point masses. So we can focus on the center of the meter stick as it falls. So that's your torque. The moment of inertia, since it's rotating about its endpoint, is 1/3 ml squared. So we have 1/3 ml squared for my moment. I've got mg sine theta L/2 for my torque, which means I can write an expression for my alpha. So alpha is the angular acceleration, which is torque over my moment of inertia, and doing some substitution, I can see that the mass of the meter stick actually does not matter, and I can get rid of one of the lengths of the actual meter stick, and my angular acceleration ends up being 3/2 g sine theta over L. And if we want to take this one step further for something we will see in the future, the definition of angular acceleration is the second derivative of our angular displacement. So what we've actually just written here is a differential equation for the displacement as a function of time as this pencil is falling. And what we'll do in the future is solve for how long it takes those meter sticks or pencils or whatever's tipping to fall over. There's a link in the description that shows you how they got the actual time, but we'll get to that further when we get into differential equations in our oscillation chapter. And the last idea we want to talk about here is this idea of rolling without slipping. We talked about the non-slip conditions, and in terms of our non-slip conditions, when an object is rolling without slipping, that means it's in contact, the bottom of the wheel is spinning, or in this case the rope is in contact and not slipping over top of the pulley. That means that whatever the linear velocity of the rope coming in can be translated into the rotational motion of the pulley by just doing omega r. And if that's the case, if the wheel is angularly accelerating and picking up speed, that means that any point on the wheel is also accelerating in a straight line due to alpha r. So those are our non-slip conditions. So let's apply that to things rolling down hills without slipping. When you have a rolling without slipping condition, let's draw what we used to do for objects on inclined planes. Let's draw a force diagram for say this ball. So if we look at this before, if there was no friction involved, then these would be the only forces acting on the ball. And if I look at that, I would say, okay, the force that's going to make me go down the hill is the component of gravity that is pointing down the hill, which in this case ends up being mg sine theta. What that's going to do is make the ball accelerate down the hill, which means that our acceleration ends up just being g sine theta, which is what we did before, which means that that ball, when it gets to the bottom here, would actually be accelerating, moving in a straight line, moving with a velocity, but there would be no rotation. If there's no friction involved, there's no reason for the ball to actually start to roll. So let's reset this problem with friction. So now when we look at the scenario with friction, we have a third force on the ball before it starts going down the hill. The First thing we want to do is analyze the ball in terms of torque. So what I mean by that is let's draw the ball and see how each force creates a torque on the ball. Alright, so our first one, force of gravity. Force of gravity is acting at the center of mass of the ball. So if you're trying to get the torque from gravity, radius times the force of gravity, there is no radius. So the torque from gravity is 0. Okay, let's look at the normal force. The normal force is acting from the ground, pushing back up on the ball. However, it's acting parallel with the radius, and if we wanted to torque the normal force, that would be radius times force times the sine of the angle between them. And since the sine of the angle between them is 0 or 180, there is no torque from the normal force, which leaves us with friction. So the force of friction is acting on the ball, and it is acting a radius away from the ball, so there is torque caused by friction. If you're trying to figure out the direction of the torque, look at how it's trying to make the ball spin. It's trying to make this ball spin in this direction, so technically it's a negative torque. So that negative torque is trying to make the ball spin clockwise as it goes down the hill. So there is torque from friction. You can take the radius times the force of friction to calculate that out. So let's reset our force formula. So the forces that are making us accelerate down the hill are mg sine theta from the ball's weight. The force of friction is fighting us, and that's going to make the mass accelerate down the hill. However, this time we want to look at the force of friction in terms of a torque making the ball spin. So the torque from friction is friction force times the radius. Moment of inertia, let's call it a solid bowling ball, so 2/5 mr squared. And we want to turn our alpha into straight line acceleration, so that's a over r. So again, we can look and see if anything's going to cancel for us. It looks like one of the radiuses does, and the radius over here from the torque. So the force of friction here is actually 2/5 ma. So we're going to put that force of friction back up into our equation and see what that does to our force equation. So we've got mg sine theta minus 2/5 ma now for the force of friction equals ma. Let's get all the masses and accelerations together. Combining 1 ma and 2/5 ma give you 7/5 ma. Again, we can cross out the masses and solve for the acceleration, and the acceleration ends up being 5/7 g sine theta. So when there was rolling without slipping, when there was no friction around and it just slipped down the track, the acceleration was just the old-fashioned g sine theta. But now that there is rolling without slipping, because the force of friction is on it, the force of friction causes a torque on the ball and causes the ball to rotate. So as the ball reaches the bottom here, the ball has linear velocity and rotational angular velocity. The reason balls roll when they go down the hill is due to a static friction force that is acting on them at the point of contact at the bottom of the ball. If there was no friction, the ball would just kind of slide down the hill and pick up speed. But now that it's rolling, it's picking up linear speed and rotational speed.